I would like to invite Professor Anil Kumar from the Physics Department in IISc to chair the first session of the conference.
Thank you, Girvin. A great pleasure to invite Stephen Girvin from Yale University to give his first lecture on circuit QED, wiring up quantum systems. And I will raise my hand in 30 minutes, say there are 5 minutes left.
Thank you. Okay, good morning. Just not try this again. Is that working? Doesn't sound like it. Okay. All right. So it's a pleasure to start off this conference. I've had a fantastic 3 days lecturing with the students. It's a bit of an unusual situation. The students in the audience are now experts on this topic, and the professors are not. But I will, and I'm also going to have to go fairly fast to cover all the things I want to cover. Possibly, I may reach my upper speed limit, which is about 0.25 Shankar velocity, but we'll see. So I'm going to be talking about experiments done at Yale by my experimentalist friends here, and these guys in particular, and some recent theoretical developments in connection with superconducting qubits and interacting with microwave photons. So quantum electrodynamics, as everybody knows, is a study of the effect of quantum fluctuations of the electromagnetic field on the properties of electrons and atoms. It leads to things like spontaneous emission, mass and charge renormalization, Lamb shifts. And one thing we can do as quantum engineers is modify the normal mode spectrum and the fluctuation spectrum of the vacuum by enclosing the vacuum in a box with shiny walls, which makes for a discrete set of electromagnetic modes whose frequency can then be adjusted by changing the size of the box so that they're the same as, higher than, lower than the transition frequencies of the atom. So you can engineer, you can, for example, get rid of this spontaneous emission by engineering there to be no modes at the frequency at which the atom wants to emit. So we're going to talk here about circuit QED. It's sort of analogous to cavity QED. It's going to involve microwave photons inside superconducting electrical circuits and, more recently, three-dimensional resonators. And instead of real atoms, we're going to have artificial atoms, which are made of Josephson junction circuits with antennas attached to them so they can talk to the microwaves. And because we can engineer the size and shape of these artificial atoms, we can make them couple incredibly strongly to the microwave fields and achieve nonlinearities that are orders and orders of magnitude larger than can be achieved by our friends in AMO physics. And one is able to do nonlinear quantum optics in electrical circuits at the single photon level. And this could be a quantum computing talk or a quantum optics talk. I'm going to make it a quantum optics talk. To build quantum mechanical electrical circuits, we want to use our usual circuit elements, but we don't really want to use resistors. They cause dissipation. We want our qubits to live a long time. But if all you have are inductors and capacitors, the only thing you can make is a harmonic oscillator, which is fine. That's a resonator. But if you want to make an artificial atom, you need a set of quantized energy levels that are not evenly spaced so that you can pick out two of the levels and have a uniquely addressable transition frequency between ground and excited state, or the 0 and 1 state of the qubit, and so you need a nonlinear element, in this case the Josephson junction, which is the only known nonlinear, non-dissipative circuit element. And it'll all be made of superconductors and all cooled down to 15 millikelvin. Characteristic microwave frequencies will be, and atom transition frequencies will be 5 gigahertz. It's handy to remember that 21 gigahertz corresponds to 1 Kelvin. So you have to be much colder than that. So here's from Michel Devereux, not to scale drawing of the hydrogen atom. You can the animation. There we go. Okay, so you can see the electron in various allowed orbits corresponding to the quantized energy levels. And you can imagine making an electrical circuit, which is an LC resonator, and it's just pairs of electrons sloshing back and forth, charging and discharging the capacitor, storing energy in the electric field here and in the magnetic field of some inductance. But of course, this is just a harmonic oscillator. It's fine for making photons inside electric circuits, but it needs to be anharmonic in order to be an atom, an artificial atom. So we do that by introducing a Josephson tunnel junction, and which acts at some level of approximation as an inductor, a large inductor connecting the two sides of an antenna. But it's a sort of nonlinear inductor and produces a anharmonic oscillator that can serve as, whose two lowest levels can serve as an artificial atom. And you can design the size and shape any way you want. The current version that we use is about 1 millimeter long. You can see it with your naked eye. And you can put it into a superposition, coherent superposition, of different degrees of oscillation of the charges back and forth. So here's a picture of 1/2 of the block of solid aluminum, which is used to make the three-dimensional cavity. There are input ports and output ports. There's a thin sheet of low-loss dielectric, sapphire here, and in the middle of that on the surface is evaporated this millimeter-long superconducting aluminum antenna with the two halves connected by a microscopic Josephson junction. And the collective excitations of this atom are just the Cooper pairs sloshing back and forth, making dipole oscillations. The characteristic dipole transition matrix element is several Cooper pairs moving 1 millimeter, which is about 10 million dBi. A little bit bigger than you can get with a cesium atom. From it's 100,000 times bigger than the transition dipole moments that Serge Haroche, who's having a good year, uses in his rather large Rydberg atoms. And so you can get the atom talking very, very strongly, exchanging energy with the cavity at rates of order 100 megahertz, much, much higher than the dissipation rates due to photons leaking out of the ports or the qubit somehow eating up the energy. Some of the experiments I'll show you took place in a 2-cavity system where you have a very high Q storage cavity that you might want to use for a quantum memory, putting photon states in there, coupled to a low Q cavity by a nonlinear element, a qubit. And this is you can use this cavity, as I will show you, to read out the state either of the qubit or the photon state of the other cavity. And people are working on multiple qubits and single cavities, and 1 qubit connecting multiple cavities, and multiple qubits now connecting multiple cavities. So it's a very interesting time with a great deal of progress. So if we're going to make an electrical circuit with quantized energy levels, and we're going to focus on the lowest two, then mathematically that's a spin a half. Can be described as a spin a half. And with two states, down and up, and superposition states of ground and excited states, with the spin pointing anywhere on the Bloch sphere. And what we're trying to do is the mole equivalent of single-spin nuclear magnetic resonance, something that's not possible with actual nuclear magnetic moments, which are extremely coherent because they don't actually couple very strongly to each other or to the magnetic coils that you're using. But it's not the magnetic moment of this object. The object itself is an electrical circuit element with an electric dipole moment to which we couple electrically. And because of that, and because of the large size of the artificial atom, we can do NMR, so to speak, on an individual atom. So here, for example, is a measurement of T1. You apply frequency tone to the atom, which is at its resonance frequency and just the right duration to flip the pseudospin from ground state to excited state, a pi pulse in NMR language. Then you wait a certain length of time. Then you measure, and I'll explain how we measure whether the qubit is still in the excited state. You repeat this measurement roughly 100 billion times, an average, and you get this nice exponential decay due to the qubit spontaneously emitting a photon and falling to the ground state. And the decay time, T1, is 103 microseconds. If this millimeter-sized artificial atom were in free space, coupled to the vacuum fluctuations in the room, its T1 time would be about 100 nanoseconds. It's 1,000 times longer because we've put it inside a cavity that has no modes at that transition frequency. So that's called the Purcell effect. It gives us a huge enhancement of the lifetime by filtering out the vacuum fluctuations from the outside world at the transition frequency.
So, Steve, what limits the 103 microseconds? One could improve it by improving the cavity measurement.
Right. So we are not completely sure what limits this at this time. There's some evidence. The two choices are the cavity still has a finite Q, and there is potentially a Purcell effect in which you emit a virtual photon into the cavity at the wrong frequency, and then it sneaks out through the output ports. Then there are other things like tiny dielectric losses in the sapphire substrate, or possibly in the Josephson junction itself, but we don't have any really solid story yet that's not obviously limited by materials at this point. So the short answer is we don't know, but the times keep getting longer and longer as we design things in ways that minimize potential sources of dielectric absorption. Is what? It's, yeah, something like that, 15 or maybe 30, something. So T1 gets longer and longer as it gets colder, and there are quasi-particles in the antenna that produce T1 effects. They freeze out at a certain scale, except that they're totally out of equilibrium. So they saturate at some scale. There are many more quasi-particles than there should be at this temperature. But it's not clear that the quasi-particles are limiting this time. So here's the other NMR measurement, the T2 measurement, the phase coherence time. You make a pi/2 pulse, which produces a coherent superposition of ground and excited state. You wait a length of time. You make another pi/2 pulse around some axis, which you continuously rotate. And that converts phase information into sigma z information, which I still haven't told you how we measure it, but that's the axis we can measure. And ignore the oscillations. That's just a particular way of doing the experiment. But the envelope decay gives you this T2 time, and this is a particular version, T2 echo, which is 145 microseconds, which is probably the current world record for superconducting qubits. So here is The length of those coherence times versus year, the first superconducting qubit being built by the NEC group in 1999 with immeasurably short coherence time, let's call it a nanosecond, and we're definitely more than 5 orders of magnitude larger than that now, going up roughly exponentially with time. And just through clever quantum electrical engineering and changing the design of the qubits and making the cavities better and so forth. And while each factor of 10 is harder than the last one, there's no clear evidence that this thing is going to stop. So we'll see in a couple of years whether we have another order of magnitude. Yeah. So there are different. So this is for one class of qubits, charge-based Josephson junction qubits. It refers to the topology of the circuit. And there are various echo techniques for eliminating the effect of low-frequency noise on the coherence times. And that just is what that refers to. Okay, so we've got the high Q cavities with Qs of up to 500 million being fairly easy to make, and no reason they couldn't be larger based on Serge-Roche's results. And we have these artificial atoms whose coherence time is no longer so embarrassing that it limits our ability to do experiments. And so I'm going to tell you about some new tools that have been developed for this regime that allow you to engineer non-classical states of qubits and photons. So it's now very easy to make photon cat states, to map qubit states onto the photon states of a storage cavity, to do so in such a way that the qubit state is mapped onto a Schrodinger cat state in the cavity in a clever way that means that if you use that as a quantum memory, it still works even if it loses photons. So that protocol has been developed. The first step in the experiment has been done, but that hasn't yet been achieved. And then based on those ideas which came from here, we posted yesterday a paper on the archive to extend those ideas to realize the topological error correction codes in this circuit QED setup. So I'm going to tell you about the kind of toolbox that's available now in this type of circuits to the quantum engineer to make arbitrary states. And it's very simple. It's based on this dispersive Hamiltonian. So we focus on one mode of the resonator. It's a harmonic oscillator. A dagger A just counts the number of photons in the resonator. We treat the atom as a two-level system with transition frequency omega q. And we detune the atom from the resonator so that the dipole coupling really only acts effectively in second-order perturbation theory and leads to this so-called dispersive coupling term, chi sigma z times the number of photons. Then there'll be some weak damping terms and some driving terms on the cavity and the qubit. But there's a very simple diagonal Hamiltonian, which is really actually sort of well known in the cavity QED world. But what's new is the size of this dispersive coupling can be hundreds of millions of times bigger than you can achieve in nonlinear media with lasers and so forth. So you'll be able to do interesting things at the single photon level, which opens up a new toolbox for making arbitrary states. So let's first let's understand this dispersive coupling term. And one way to view it is that, the coefficient of A dagger A, which is the resonator frequency, gets modified. It's now omega resonator plus chi sigma z. The cavity frequency now depends on the state of the qubit. And it can be omega r minus chi if the qubit is in the ground state, or omega r plus chi if the qubit's in the excited state. And what's new is that this can be thousands of line widths of separation because of the strong coupling that can be achieved. So what can you do with that? Well, if I were to send a microwave pulse at this frequency, it would excite the cavity into oscillation mode and fill it with photons if and only if the qubit is in the ground state. If I send a microwave pulse at this frequency, it will excite the cavity only if the qubit is in the excited state. So that gives us our first tool, conditional displacement of the cavity oscillator, setting it into motion, conditioned on whether the qubit is in the ground state or the excited state. So that allows us to entangle the cavity and the qubit. So for example, if the qubit starts in the ground state, cavity in the vacuum state, I apply this drive pulse, then I will get a coherent state alpha, which I describe in this quadrature picture. Alpha is a complex number. And this is the cosine omega t quadrature of the electric field, and this is the sine omega t quadrature of the electric field. And the qubit remains in the ground state, but the cavity fills with this coherent oscillation. On the other hand, the same tone applied when the qubit's in the excited state, the cavity is now off resonance, and it just stays in the vacuum state. Nothing happens. So what happens if the qubit is in a superposition of ground and excited state? Then the cavity is in a superposition of having two different resonance frequencies. That should start to bother you now. I apply this tone, and for the part of the wave function where the qubit's in the ground state, the cavity fills up with 100 photons. And for the part of the wave function where the qubit's in the excited state, the cavity stays empty. And 100 is, I'm not exaggerating, 100 photons. So you make this bizarre entangled state, and this is a true Schrödinger cat, okay? The cat is dead and the poison bottle is open. The cat is alive and the poison bottle is empty, right?
So 100 just happens to be the number for this particular...
Well, it's been done up to 100 photons. Yeah. And in the data, I'll show you that there was an intermediate step where it had actually 100 photons in it. Now, the rate at which you lose photons from the cavity is 100 times the line width at that point, so that's why it's great to have very high Q cavities. So people sometimes think of the Schrödinger cat as the cat is, superposition of dead and alive, but it's actually the correct description is this, that it's entangled with the state of the poison bottle. Okay? All right, so just to summarize, we have tool number one is conditional displacement of the cavity to an oscillating state filled with photons, conditioned on the state of the qubit. So you can make these nice entangled Schrödinger cat states. Okay, so now let's get tool number two, which is conditional flip of the qubit conditioned on the state of the cavity. And it comes from the same Hamiltonian and from the very same term, but we just rearrange our parentheses, our interpretation here. We say, oh, it's not the coefficient of A dagger A that changed by sigma z, it's the coefficient of sigma z that changed by A dagger A. So the frequency of transition of the qubit is its old value plus 2 chi times the number of photons in the cavity. And that's called the light shift of the qubit transition frequency. And by the way, stray photons entering the cavity will totally dephase the qubit through this mechanism, so we have to be careful about that. So here is a picture of I still haven't told you how I should say this effect, which I just described, where the cavity frequency depends on the state of the qubit, makes it possible to read out the state of the qubit. You just apply a tone to the cavity and see where it resonates, and that allows you to read out the qubit. So that's how you do spectroscopy. You apply a tone to the qubit, then you use the cavity to read out the state of the qubit. And if the qubit is coupled to a cavity that has a coherent state in it, it'll be in a superposition of 0, 1, 2, 3, 4, 5, 6, 7, 8 photons, and it will have a different transition frequency for each case. And if you average the absorption spectrum over a long time, you will see a peak at corresponding to each one of those possible photon values. And you see they're well separated, and actually their separation is in units of line width is 100 times bigger than it looks here, because these lines have been power broadened to make the measurement easier to do by about a factor of 100. So this is, again, about 1,000 line widths here. Yeah. 150 dB of shielding, of filtering, dissipation, and it has to be cold, otherwise the black body radiation from the 1 Kelvin stage would kill you. The fact that Rob Schoelkopf started life as a radio astronomer is actually helpful. Yeah. So this data should convince you that microwaves, despite their name, are particles, and that despite the fact they have 100,000 times less energy than the photons from this light, you can count them, and they're particles. Okay, so now that we see that effect, now how can we use that to get a new tool? Well, here's the spectrum of the qubit, and if I were to apply a pi pulse to the qubit centered on this frequency, it would work and flip the qubit if and only if there's exactly 1 photon in the cavity. Or if I applied it here, it would work if there's 0 or 2. So I can conditionally flip the qubit dependent on the particular state of the cavity. So there's this children's card game called Go Fish that people play in the U.S. So Rob Schoelkopf calls this Quantum Go Fish. Got any 1s? Got any 0s? Got any 2s? And you can, again, do the, instead of displacing the cavity dependent on the state of the qubit, you can flip the qubit dependent on the state of the cavity. So those two tools together permit you to do entangling gates of multiple qubits in a cavity, and now make it, I'm not going to go into the details, but I showed you how to make a kind of true Schrodinger cat entangling the cavity with qubit, but it's possible to make pure photon Schrodinger cats where you unentangle the qubit from the cavity and end up with a superposition of 2 different cat states. And it turns out now to be relatively easy to make and to show that you've made them using these 2 tools. What you'd like to do is map the qubit state, let's say a superposition of up and down with some phase, and the cavity and the vacuum state, onto qubit being in the ground state, so unentangled from the cavity, but a superposition of 2 different coherent states of opposite phase. There are 2 phases here, the phase of the coherent state and the phase of the superposition. It's a little confusing. It's easy to make a mixture, but if it's a coherent superposition, you should be able to detect what the phase of that superposition is. So in this quadrature representation, you have a blob over here representing 1 coherent state, a blob over there, and the cavity is either oscillating with this phase and amplitude or that phase and amplitude, and the 2 are superposed with some well-defined quantum phase, this guy. So so using those 2 tools, you can make such a state. I'll skip over the details. And suppose you put a plus sign. You start with the qubit having in the x direction, and then the photon coherent state inherits that plus sign. Well, that's, if you think about it, like a harmonic oscillator in some state with weight over here and here, that's a completely symmetric wave function. And so it can only be made up out of, it has definite parity, and it's even. So it's only made up out of even photon numbers, 2, 4, 6, 8. If you put a minus sign there, then you should only get 1, 3, 5, 7 photon states, and it works. So that's some indication that it's not a, if you had an incoherent mixture, you would get both. So that's some indication that it's a coherent cat state. More complete indication is to try to make the Wigner function, which is kind of a quasi-probability distribution in this quadrature space. This is kind of like position of the oscillator. This is like momentum of the oscillator. It's the two quadratures of oscillation. And this is not the probability, because you can't measure position and momentum at the same time, but you can define this Wigner function, which isn't always positive. It can be negative, indicating you have a non-classical state. But it measures something like the phase space distribution of the state. And it turns out to be easy to make such a measurement using these tools I just described. Again, I won't go into the details. So here is an example of a Schrodinger cat state with two coherent blobs, this one and that one, each with average photon number 7. Maybe it's my cell phone. So it's a relatively large Schrodinger cat. And you see here in the center some what effectively are two-slit interference fringes from those two slits. And you see the color is giving negative and positive, these rapidly oscillating fringes. And the fact that it goes negative, well, the fact that there are fringes means that there's a well-defined quantum phase of the superposition. And the fact that it goes negative means it really is non-classical. So the color scale is the amplitude of the Wigner function. Oh, what's actually measured experimentally? So the way you measure the Wigner function is you 5 minutes. You take the state and then you displace it coherently with a tone some distance, which is the location here in this graph, and you measure the parity of the resulting photon number. One photon out of it, the sign of all those fringes reverses. And so the fact that you can see them means that it's a really stringent test that you have coherent state. And of course, the rate at which you lose photons scales with the number of photons.
So how long does this last? How stable is it? It's much shorter than the coherence time, this 100 microseconds.
Well, it's so the coherence, no, so this is in the cavity, right, which has a much longer
it's in the cavity.
Yeah. So the best cavities that we have line widths of 10 hertz. So, but this is shorter than that.
But for the order of a fraction of a second.
Well, so this is these cavities. I've forgotten now. So let's say quarter millisecond, and there's a 7. So let's say 100 microseconds. So then they started playing around. Came up with this nice cat. So still need a little work here.
You're sure it's not an H?
It's absolutely not an H. I can guarantee that. Okay, so let's. Let's do a scan down, a line scan here to see those interference fringes. Because for the really large cats, you can't do the whole plot. So here's a cat with 4 photons on average, 7, 10. You see the fringes are going faster and faster because the 2 slits are getting further apart, so to speak. And here's one with 25 photons. And in the intermediate step of constructing this, where you had an entanglement between the qubit and the cavity, there was an entanglement between no photons, qubit in the ground state, and 100 photons, qubit in the excited state. And then you unentangle the qubit, shift things around, and you end up with 25. So this is, as far as I know, probably the largest, most macroscopic object ever put into a coherent superposition. We were making Serge Roche extremely nervous, but now he can relax. So once you can make these four-legged cats, you can do this amazing trick that these guys thought up of mapping the qubit state not onto just a single cat, but a four-legged cat in such a way that if the quantum memory ever loses a photon, and you get a minus sign here, you also get a minus sign here, and you can reconstruct the state of the qubit even if you've lost photons. It's a very clever idea. And so it's a kind of error-correcting quantum memory, which is robust against photon loss. And then we've built on those ideas to think about a way to measure the four-spin stabilizers that you need to realize these topological quantum error correction codes. That's described in this here. And experiments, I hope, will be forthcoming on this in the next year. So I'm out of time, so I'll skip over the details of the proposal and just summarize by saying that this very simple dispersive Hamiltonian, but with extremely strong dispersive coupling of thousands of line widths, allows us to entangle qubits with cavity, map qubit states onto photon cat states, make, in principle, error-correcting quantum memories, and perhaps in the future do topological quantum computation. So I'll stop there, and thank you very much.
Nice talk. Very impressive. I do NMR from Place Quantum Computing. There have been a lot of questions, but still we'll take a few questions from floor.
I have a question about these various cat states that you had a different number of photons.
Yeah.
Is there any prospect for attempting to answer the question that a lot of people think are very deep and very important, that how the decoherence depends on number of microscopic objects in an entangled system, you know?
Right.
Because is it exponential? Is it Paul law? It of course depends on the details, but it seems that there is information there, right?
Right. So certain people like Tony Leggett have some ideas
Well,
of how you define macroscopic.
Yeah.
I'm a simple guy, and I'm pretty sure that for these photon cat states, the loss rate just goes like the mean photon number.
Okay.
And because each time you lose a photon, as I said, you flip the sign of those interference fringes. And based on at least up to this scale, it's entirely consistent with the decoherence rate being the mean photon number times the cavity decay rate. But it's this is, you know, as I said, perhaps the most macroscopic case in which that's been tested. And so far, quantum mechanics seems to be working fine. But it's a very interesting possibility to make really macroscopic things and see whether somehow the decoherence.
Of course, Tony is very clever. Every time that number increases, he increases the number where the transition is going to take place.
Right. So one, you know, what is the limit here? Well, one is that the decoherence rate goes up faster and faster.
Yeah.
That makes it harder to do the experiment. Another is that I left out a few small terms in the Hamiltonian, such as the nonlinearity that the cavity inherits from the qubits, so you can get some little squeezing that kind of distorts the shape of the cavity and stuff. But as I said, we could get up to superposition of 0 and 100 if you move fast.
When you talk about the photon cavity state, how the 2-bit at that time, the state of the 2-bit at that time.
So how do we? So I showed. I'm not sure if I understand the question. I showed you in the first toolbox set how to entangle the qubit in the cavity, and then I didn't show you, but using that second tool, you can unentangle the qubit from the cavity, leave it sitting in the ground state while the cavity is in this superposition state.
There are no more. Oh yeah, there is one more.
I have a question about the error correction you mentioned at the end.
Yeah.
So by going to a four-legged cat, being able to error correct to like relatively small overhead? Is that because you're only correcting for a restricted set of errors?
So the question is, about using the photon state stored in the cavity as an error correctable memory. So there are two things to comment. So you need to have a certain number of qubits if you're doing a regular error correction code, and 5. So that's a Hilbert space of 2 to the 5. And the cavity has an infinitely big Hilbert space, so that's what makes it possible. But this particular protocol relies on the assumption